All right, so where we left off, we were talking about collected over water problems. So when you collect a gas over water or through water, right, what we talked about was a little bit of water is going to get trapped in that gas collection jar. And when that happens, the water molecules that are present are part of the collisions, right? So they're part of the pressure. And that pressure in the jar, typically that's going to be equal to the atmospheric pressure in the room. Because when we collect the gas, we're not pressurizing it or do anything to it, right? It's going to probably be equal to the ambient pressure. So that pressure in the reaction vessel or the collection jar, whatever you're using or however it's being done, that collection jar pressure is equal to the atmospheric pressure, which is really equal to the pressure of the gas that you're collecting and that little bit of trapped water particles that are inside. So basically, all of that to summarize quickly, when you see a question that says the gas has been collected over water, all I want you to think about is to say, okay, I'm going to take that initial pressure that's given to me and I'm going to subtract the vapor pressure that's due to water at that particular temperature. That's the good thing about these types of problems is that the pressure due to water, called the partial pressure of water, is temperature dependent. So as long as we know the temperature of our particular reaction, um, just like on this example, it was 17 degrees Celsius, we can go to a table and look up what is the vapor pressure of water at 17 degrees Celsius. In fact, you'll have to do that on your homework. And then that's the pressure due to water. But just know that if you're at a different temperature, the vapor pressure of water is going to be different. And we're going to see that in the next example. All right. So in this example, it says we've got a sample of potassium chlorate, which is KClO3. It's heated and it decomposes into potassium chloride and it releases oxygen gas. The oxygen was, there's that phrase, collected over water. We're at 21 degrees Celsius, right? So different temperature than the last example when we were at 17. Okay, so there's my temperature. Notice the vapor pressure of water at this temperature, 21 degrees Celsius, is different than the one that we saw earlier. In the last example, lower temperature, less water bubbles up. If you're at a higher temperature, the more water is going to bubble up, which means that the vapor pressure of water increases with increasing temperature. And we know that relationship, right? If I look at the P1V1 over T1 formula, pressure and temperature are directly related, right? So if temperature goes up, pressure goes up. All right, so we have a different vapor pressure of water. These vapor pressures of water, remember, these are constants. This is given to us in this question, but if it were a homework problem, you would go look at the table and you would say, okay, at 21 degrees Celsius, that's the pressure due to water. All right, so anytime it says collected over water, we have a little additional step here. Because again, the oxygen that's being collected, there's a little bit of trapped water inside of that collection jar, and we need to mathematically remove it. And we do that by subtracting the pressure. All right, so the pressure in the room, the 746, that's 746 millimeters of mercury, which is the atmospheric or barometric or ambient, right? That's the pressure that's inside the room, which we assume again is the pressure inside the collection jar. That is the total, right? That is both gases, the oxygen and the water. So we need to subtract that pressure due to water, which again would come from the table, right? In this case, we went ahead and just gave it right here in the question. Quiz questions. You may, for some of them, if it says collection over water, there's going to be a vapor pressure chart given to you, similar to what we're going to do in lab as well. So just make sure at 21 degrees Celsius, if you had to go look at the table, this is where we get our pressure due to water, right? So the pressure due to water is it's kind of a constant at that temperature. So I hate to say constant because of course it changes with temperature, but it is temperature dependent. As long as we know what temperature we're at, we know the pressure due to water. Okay, so if I do that first subtraction step, you can do your decimal place rule now if you want, or you can wait and at the end look at your significant figures. But this is going to be the pressure of just the oxygen, which is 727.3 millimeters of mercury. And again, I got that by subtracting those two pressures. All right, so always when it's collected over water, take the original pressure that's given, subtract the pressure due to water to get just the pressure of the gas that you're collecting. So mathematically at this point, we removed the water from that collection jar. All right. Now, what else do we know? So as we've got a volume of 155 milliliters, that was the volume of oxygen that was collected. Again, we know our temperature, 21 degrees Celsius. And like we talked about when we started gas laws, in order to understand how much oxygen, like in terms of moles, we're actually collecting, gases are dependent, like the amount of the gas is dependent on three variables, right? If I'm going to really understand how many molecules of oxygen or moles, right? We like the substitution of moles are collected, the volume doesn't tell me everything. You know, with the solution in molarity, volume gave us everything we needed to know. We could figure out moles if we had molarity. But with a gas, volume is flexible. So we could squeeze the volume and still have the same number of moles inside. So volume doesn't give us enough information. We also need to know temperature and pressure. Now, a lot of times students that had intro chem and got really used to using that 22.4 conversion factor for gases, you want to remember that if you're thinking along those lines, that 22.4 only works at STP, right? And if you're like, I don't remember what she's talking about, it's actually best. Like it's that number, the constant, I kind of went through this last week on Thursday, that 22.4 liter per mole conversion, it comes from Pivnert, but it only works at STP. And very rarely are you going to be at STP, right? Standard temperature is 0 degrees Celsius. That's cold, right? And it's very rare that you're going to do your experiment at that temperature and perfect atmospheric 1.00 atm pressure. So the 22.4 really doesn't work very often. So to me, why memorize it? So instead with gases, right? We know we're going to do stoichiometry. The question is asking us to get the mass of the potassium chlorate, right? How many grams of potassium chlorate did we decompose in order to get this much oxygen gas? You know, if you're going to do stoichiometry, right, we're going to have to go through the mole ratio, looking at the quantity in this case that we produced, and then back calculating to figure out the quantity that we reacted, right? So oxygen is our starting point, and then potassium chlorate is where we're headed. Now, if we want mass, like we've talked about, we know molar mass is going to get us there. So we're going to need the molar mass of a potassium, which is 39.10, a chlorine, 35.45, and then 3 oxygens, which would be 48. So the potassium chlorate has a molar mass of 122.55 grams per mole. All right, so I just added up that real quick from the periodic table. All right, so what do? With gases, we had talked about in stoichiometry, it's not a simple conversion to get us from volume to moles, right? Because again, volume is dependent on pressure and temperature, right? They're all connected. If it were something where we had the mass of oxygen, molar mass would get us to moles. Again, volume of a solution, molarity would get us to moles. Gases are harder though, because in order to get moles, we're going to have to go through PV equals nRT. So it's not a real pretty conversion factor, right? We're going to have to go through Pivnert. We're going to have to get the moles of O2 first. If I divide both sides by RT, I'm going to find the moles of oxygen. So N is moles, O2, right, is equal to pressure times volume divided by R and temperature. Now remember that R constant, the 0.08 to 06, the units are picky. So your volume has to be in liters. And of course, ours is not. It's in milliliters. All right, so we're going to come over here and we're going to make volume in liters after dividing by 1,000. It's 0.155 liters, just moving the decimal 3 spots to the left. Pressure has to be in atmospheres. So I'm going to take that 727.3 and divide it by 760. That's the conversion. So pressure here is really 0.957 atmospheres. And then temperature, as we're, I think, probably very used to at this point, has to be in Kelvin. So once I add 273, we get 294 Kelvin. Now, if you put the 0.15 on it, that's fine. You can keep it. Your calculation at the end, your number might be just slightly different than mine, and that's okay. As long as at the end you round to the correct number of significant figures, that's fine. All right, sorry about that. There we go. Okay. So now I've got the pressure, volume, temperature in the correct units. I can solve for my number of moles. All right, so my moles of O2 would be my pressure, 0.957, my volume, 0.155 liters, divided by 0.08, 206, and temperature of 294. All right, so I'm going to take my 0.957, multiply it by 0.155, divide by 0.08, 206, and then divide by 294. I'll keep 3 sig figs here. My moles of O2 is 0.00615. All right, now that's my moles of oxygen gas. So after all that, I'm like halfway there. All right, now the rest of it I think is probably the easier half. All right, so we found our moles of oxygen, which is our moles of A, right? So now if we're going to try to get back to moles of B, potassium chlorate, that's just going to be where we bring in that mole to mole coefficient, right? The ratio. So this is really part 1 all the way over here on the right. So this is really part 2 on the left. Okay, so we're picking up where we left off, 0.00615 moles of O2. From the balanced equation, 3 moles of O2 would have come from 2 moles of potassium chlorate. And then to get to grams, like we found from the periodic table, 122.55 grams is the molar mass of the potassium chlorate. So I'm going to take the 0.00615, multiply that by 2, divide it by 3, and then multiply that by 122.55. So the calculation told me I would have started with 0.502 grams of potassium chlorate in order to produce that 155 milliliter sample of oxygen gas at 21 degrees Celsius and an ambient pressure of 746 millimeters of mercury, which of course meant a partial pressure of oxygen of just 727.3. Okay, so because it was collected over water, we take the given pressure that's reported, get rid of the water, mathematically subtract that from pressure using the vapor pressure of water. That gives us the pressure of just the oxygen gas. So that's the signal, right? When you see anything collected over water. So what we did first is we said, okay, if we've got that partial pressure of oxygen, that volume of oxygen, that temperature of oxygen, let's use PivNert, making sure the units are in the right liters, atmospheres, moles, Kelvin, and let's find moles of oxygen in this sample. So we know with that partial pressure and that volume and that temperature, there would have been 0.00615 moles of oxygen collected. All right. Uh-oh, today's going to be one of those days. Okay, sorry. All right, so we've got moles of O2. Then we do mole ratio, getting rid of oxygen. So 3 moles of oxygen on the bottom, 2 moles potassium chlorate on top, and then molar mass of potassium chlorate from the periodic table to get us to grams. All right, so a little back calculation. We knew how much we produced, so how much did we start with? And some familiar things, anytime we're looking for mass, we know molar mass is our pass-through. If we're relating two things in a chemical equation, we know we've got to go through the mole ratio. What's different now for gases for stoichiometry is we don't have a pretty conversion factor like we do for solids, where molar mass just goes right from mass to moles or moles to mass. We got to do all this with PivNert and then find moles, and then we can do what we've got to do. So PivNert is the pass-through with gases, not molarity for solutions, not molar mass for solids. You got to go through PivNert because, again, when we first started talking about gases on Thursday, I said every gas law problem, just start by asking yourself, what formula should it be, right? And that formula is either going to be P1V1 over T1 equals P2V2 over T2, the combined gas law, or it's going to be PV equals nRT, which I always call PivNert. That's the ideal gas law. PivNert is the one we want to use here because, of course, it's got moles in it, right? And we know if we're going to do any kind of stoichiometry, we're going through moles. So you knew starting this question that you were going to be using PivNert. So with stoichiometry, right, anytime we've got a reaction that's occurring and relating two substances in the chemical equation, we know that we're going to go through PV equals nRT. So a little flow chart, if it helps. Again, the whole flip book analogy really, that came to me after I had children. But if we're looking for moles of A, right? We learned that for solids, we're probably going to measure the mass of that, right? If we walk in the lab and we're dealing with potassium chlorate solid, we're probably going to measure how much mass we use. That conversion to moles is the molar mass from the periodic table. Now, with volume, you got to be careful because volume of what, right? If we're doing a solution, something that's marked aqueous, what we saw is molarity is our way to get to moles, and that'll be given to us in the chemical equation because it's dependent on the solution that we're using, right? So it always told us the molarity of the solution. If it's a gas, right, then to get to moles, we have to use PV equals nRT. All right, so sorry, that looks like that didn't come out right. Sorry. PV equals nRT. There we go. All right, so not a nice simple conversion step like molar mass or molarity, but if it's a gas, right, you got to go through PV equals nRT. The only other substance type we've got, right, solids, liquids, gases, solutions. If it's a pure liquid, typically what we would do for that volume of a pure liquid, something that would be marked L in the chemical equation, then molarity doesn't apply because it's pure. And molarity's that's only is for a mixture, right? It tells you the amount of solute inside the solvent. So aqueous, right? That's a solution mixture. But if it's a pure liquid, something that's just marked L in the balanced equation, again, you're probably going to use volume because it's a liquid, but you can first convert it to mass using density. All right. And we saw a little bit of that way back when. So that's our flow chart for the 4 different substance types, right? Solids will have mass, liquids will have volume, use density to get to mass. We'll have gases where PIVNERT, it's coming back, is our pass through, and then is solution. Those are our 4 ways. All right. So that's our kind of half of our flow chart. Obviously, the middle of all stoichiometry is to convert A to B. And then from there on the right side, it would look just like it does on the left. Where we headed? Do we want mass like we did with potassium chlorate? Molar mass is our pass through. All right, so let's do some more stoichiometry questions. On the next page, we've got another decomposition reaction. This time it's calcium carbonate, and we want to know how many liters of CO2. We are at 825 degrees Celsius. We're at a pressure of 754 torr, and we want to know the volume that we're collecting if we're decomposing 45.8 kilograms of the calcium carbonate. So what's different here is I don't see anything that says collected over water, which is good. That means I do not have to worry about subtracting the vapor pressure of water. But the idea that we used in that last example that we're going to use again is if we're going to relate volume to temperature and pressure, and somehow in this we've got moles because we know it's stoichiometry, then again, what formula would we use? It's going to be PV equals nRT. Now, in this question, we're looking for the CO2. So this is our B. This is where we're headed. The calcium carbonate would be where we're starting. So mass is pretty straightforward. Like always, we need molar mass to get us to moles. So calcium carbonate, if I add 40.08 for calcium, 12.01 for carbon, and then 48 for those 3 oxygens, I get 100.09 grams per mole for the molar mass of the calcium carbonate. All right, so this is going to start out, I think, pretty familiar. We're going to start with our mass, 45.8 kilograms of calcium carbonate. Now, because it's kilograms, we're going to have to change it to grams first. So 1,000 or 10 to the 3 grams per kilogram. Now, molar mass, 100.09 grams per mole. All right, so we took mass of A and we converted it to moles of A. Now we need to go to moles of B. And we know the mole ratio is always that center step, right? This is all looking very familiar. In this case, it's a 1-to-1. Balanced equation says for every 1 calcium carbonate, we're going to produce 1 CO2. So there's our mole to mole ratio from the balanced equation. All right, now from here, this is where it gets a little bit different. So like we were talking about on that flow chart, if all we wanted were mass of CO2, molar mass would get us there. But we want volume, all right? So with volume, you're going to be looking at a couple of possibilities. if it were a solution, right? And you saw that in the chemical equation and it said AQ, then you're going to think, okay, molarity. And molarity would be there somewhere for us to sort of trigger us to know to use that. But because it's a gas and we want volume, that's how we know we've got to head through, we got to go through PV equals nRT. So we actually stop here. So you'll notice that gas law stoichiometry problems, they have two parts, right? In this case, we're going to get moles of the gas first, then we're going to plug into Pivnert and solve for volume. In the last example we did, just compare and contrast, right? It was backwards. We knew all the things we needed to know about the gas. So this was part one. And then once we figured out our moles, then we could take it and go into part two. But anytime you do gas stoichiometry, it's basically two parts. So in this case, we knew all the product. So we got moles first, moles of A, then moles of B, and then mass of B. We're doing the opposite here. We have mass of A, go to moles of A, go to moles of B, but we're going to stop here because this is our N. All right. And this will be the end of part one. So if I take 45,800, divide that by 100.09, I'll worry about, let's see, we're going to have 457 point, I'll do 6, and then we'll do our 3 sig figs at the end. So this would be our moles of CO2. All right, so 457.6. Now part two. Okay, now if we're trying to relate that to volume, that's where Pivnert's going to come in. So if I want to solve for volume, dividing both sides by pressure, we'd have nRT over P. Remember, the units are picky. So we have to make sure that because of that R gas constant, temperature is in Kelvin, which of course it's not. So 825 converted to Kelvin. Temperature, let me put it up here, is really 1098 Kelvin, keeping the same decimal place, right? Not the sig figs, but decimal place. So we'll keep it as 1098. And the pressure, 754, we're going to divide that by 760 to get it into ATM, and we get 0.992. Okay, so now to solve for volume, we have 457.6 moles, R 0.08, 206, temperature in Kelvin, 1098. And then we're going to divide that by our pressure, 0.992. All right, so I will take my moles, 457.6 times 0.08, 206, times 1098, divide that by 0.992. And if I keep 3 significant figures, just showing you what I got on my calculator, I'm going to go 41600. So 41,600 liters of the CO2 gas. Okay, which is a lot, but we had a lot of calcium carbonate. All right, I'm sorry. Today's just one of those days where the video is going to keep cutting out. We'd been doing so well. All right, so 41,600. If you want to do scientific notation, 4.16 times 10 to the 4. You're not forced to. It's only if you want to. All right. Now, that 22.4 that I was mentioning earlier, I just want to kind of, if you were like, well, that kind of sounds familiar, but I'm not sure what she's talking about. I'm just going to show you one really quick. All right. And so I'm going to do the exact same question, but I'm going to change it to conditions of STP. All right. So if we're at STP, what we know is 1 mole of any gas is 22.4 liters of space. All right. Doesn't matter. Really, this should be Avogadro's number because this was really where his theory was. So it could be CO2 gas. It could be hydrogen gas. It could be oxygen gas. Doesn't matter. 1 mole of it because it's mostly empty space. There's no intermolecular forces with those gas molecules attracting or repelling each other. Collisions are perfectly elastic. We're going to talk about that here in the kinetic molecular theory. In order for that ideal gas to behave ideally, this number is true. As long as we're at standard temperature, 273 Kelvin, standard pressure, 1 atm, 1 mole of any gas is 22.4 liters of space. So what you could do with this is now this looks like a really nice conversion step. So it's going to start out looking the same. You have 45.8 kilograms of calcium carbonate. We're going to convert that to grams first by multiplying by 1,000. We're going to use the molar mass here to go to moles of calcium carbonate. Then we've got our mole to mole ratio. 1 mole of calcium carbonate goes to 1 mole of CO2. So everything that we're doing in this question is exactly the same so far as what we did in the last question. But because we're at a different temperature and pressure, even though we have the same number of moles, the volume will be different. And so that's the whole thing with gases, right? If temperature is super high in this first one, 825 degrees Celsius, now we're talking about 273 Kelvin. So instead of 1098 Kelvin, we're down to 273. We're at a much lower temperature in this example, which means we're going to have a much less volume, right? Pressure is about standard. 1 atm is standard. This is pretty close, but we do expect at least the volume to be less because temperature is less in this example. So I am not a big fan, I think I've told you this, of memorizing constants. If I can get by without memorizing things, I think it's going to be better for me. So I would treat this problem the exact same way I treated the last problem. And what I would do here is I would still be plugging in the 457.6 moles. I'd still be plugging in 0.08206 for my R constant. Temperature now at standard is 273 and pressure standard is 1. So I would still go through Pivnert. But if you like memorizing constants, and you might remember this from intro chem, what you could use here is a little bit of a shortcut, which is for any 1 mole of any gas, right? In this case, carbon dioxide, 1 mole of it, because we are at STP, that's the key. It's got to be at STP. It would occupy 22.4 liters of space. So the problem again that I have with that constant is you're not going to be at STP very often, right? But if you are, you can use the shortcut, and that's that 22.4 constant. So remember we said much lower temperature, so we have much lower volume. So it'd be 10,200 to 3 sig figs rather than 41,600 liters. All right, so again, that's the key with the 22.4. It seems like it's going to simplify your life, but it only works when you're STP. Okay. But remember, you don't have to memorize 22.4. If you're at STP, that just means your temperature is 273 or 273.15 Kelvin, and your pressure is 1.0000 atm, right? It's a perfect one. Won't limit your sig figs. So up to you. But if you do see STP, you can use this shortcut, right? But you have to be told that you're under conditions of STP. So as I was talking about, right, in order for the ideal gas law, PV equals nRT, to really work, the kinetic molecular theory has to hold true. So the size of the gas particle is negligible. So if I'm looking at a volume of gas, the volume that's actually occupied by the gas particles is mathematically insignificant, right? It's such a small percentage that it wouldn't really factor in. Because I remember when I was thinking about the collected over water problems, I remember thinking, okay, you're subtracting it from pressure, but why wouldn't you subtract it from volume too? And that's why the volume of the gas particles compared to the actual volume of the sample is mathematically insignificant. It would not matter. So that's the first thing. Gases are mostly empty space, right? The gas volume particle, right? The particle volume does not mathematically factor in. The kinetic energy of the particle is proportional to the Kelvin temperature. So the hotter the gas is, the higher the kinetic energy. Energy is, right, our energy of movement. That makes sense. More energy, it's going to move faster with greater energy. Molecular collisions are perfectly elastic. I talked about that a little bit on Thursday. That just means that as those particles collide, they don't lose any energy. So if you think about like two cars colliding, they come to a stop. Gas particles, they just keep on moving. They don't have any attraction or repulsion from each other. So no energy is lost or gained from that collision. They just keep bouncing and bouncing and bouncing. All right. So ideal gases behave that way. In order for PV equals nRT to work, then those components of the KMT have to work, right? They have to be true. So you have something called a real gas. And that happens only under extreme pressures and temperatures. When pressure gets really, really high, that signals us that those gas particles are probably really close together and the collisions are all the time, right? And then you start thinking, okay, well, if they're colliding that much, then there's really probably not very much empty space. So now the volume of that gas particle probably does play into the volume of the sample. It probably is significant now. And that's true. The other time this happens is when your temperatures are extremely low, because what we know is that as temperature drops, volume drops. So if temperature starts to get extremely low, then that means those gas molecules are huddled together, right? Really close by. I used to think they're huddled together for warmth. And then again, now all of a sudden, there's not a lot of empty space. And now the volume of that gas particle, it is significant compared to the volume of the sample. But this only happens when you're really at extreme pressures and temperatures, really high pressure or very low temperature. And then you get something called a real gas. And there is a formula to help you convert, make some adjustments for real gas behavior, but we're not going to be at extreme pressures and temperatures. So we're going to just stick with PV equals nRT. Now, velocity, diffusion, effusion. Velocity is speed, right? So it is inversely proportional to molar mass. What that means is that if your molar mass goes up, the particle gets heavier, your velocity goes down. All right. And so heavy molecules move slower. All right. So heavier molecules, meaning higher molar mass, move slower. All right. The lighter it is, the faster it goes. So if I gave you a list of gases, let's say we've got hydrogen and we've got oxygen and we've got chlorine. If I wanted to know which one was the fastest, well, hydrogen has a molar mass of 2, right? So this is our fastest in terms of velocity. Oxygen's about 32, chlorine's about 71. All right, so the chlorine with the highest molar mass, this one would be the slowest. Okay, so molar mass and velocity are inversely related. If one is up, the other's down, right? Diffusion and effusion, those basically kind of mean the same thing. The definition is a little bit different. Diffusion is when a gas spreads out into another gas to occupy the space. So like if I had a container of oxygen and I hook it up to a tank of hydrogen and I open the valve, that hydrogen will diffuse into that oxygen sample, that volume. All right, come back. There we go. So diffusion is just movement where the gas spreads into another gas. Effusion is when it flows through a small hole in the container. All right. So imagine opening your 2 liter of Coke and you have that gas come out. Technically, you could kind of think about that as effusion because the gas is leaking through that now hole. But you could also kind of think about it as diffusion because it's spreading into the surrounding air. So I don't get too picky about these two, but the idea is they're both gases that are under some kind of pressure. You open a valve or you open it, expand it into another container. So effusion is going through a hole, diffusion is just going into another space. Graham's law of effusion just means that that rate of effusion is again proportional to the inverse of the square root of the molar mass. You might see these in the dynamic study guide, but I'm not going to do any calculations with these. It's going to be the same as what we just talked about here. So a heavier gas like chlorine is going to effuse a lot slower than a light gas like hydrogen. And I know this is a little bit of an aside, but I remember this so clearly from my Chem 1 lecture back at University of Florida. Dr. Sodden, I'm not sorry, Dr. Sodden, I am drawing a blank. Oh my gosh, my brother he really didn't like this teacher and I absolutely loved him. And I'm drawing a blank. Okay, it doesn't matter. So in one canister, he had ammonia gas. And then in another canister, he had chlorine. And they were hooked up together through glass tubing. But there was a valve here that kept the chlorine where the chlorine was, and there was a valve here where the ammonia was kept where the ammonia, right? They were kept in each of their canisters. And he starts out by saying, okay, we got ammonia over here, we got chlorine gas over here. If I open the valves at the same time, when they meet, they form a white cloud of ammonium chloride. So where do we predict that white cloud to form? Well, the chlorine molar mass, again, is about 70.9, so about 71 grams per mole, right? And then the ammonia, the molar mass, is about 17 grams per mole. So what we can predict is the ammonia is going to move faster, right? It's a much lighter gas, so it's going to diffuse or effuse, right? Once I open that valve, it's going to move more quickly. So he opened both of the valves, and sure enough, we saw the white cloud form over here because the chlorine moving much slower, it didn't get a chance to go as far as the ammonia did. All right, so that's all we're looking at here is just kind of relative velocity to molar mass. I'm not going to worry about any specific calculations. Just want you to remember the heavier the gas, the slower it's going to go. The lighter the gas, the faster it's going to go. All right, but it's weird what things I can remember because there's a lot of things I don't remember so well anymore, but that one, for some reason, that one really stuck. Okay, so what we have now is the end of chapter 6, and we're going to be going into chapter 7, which is thermochem. The good news is thermochem is finally new material. We haven't really had a whole lot of new material, just a little bit sporadically in some of the chapters. So we're finally going to get to something that is probably completely new. All right, thermochem, right? You might be thinking, okay, thermo, temperature, chemistry. So what we're going to be looking at here are energy changes of chemical reactions, whether something is exothermic and endothermic. How do we predict that? How can we calculate it? And then if we know that we get energy from a reaction, like let's say the combustion of octane that fuels our car, right? That combustion reaction is what gives our car the energy to go. Can we then calculate exactly how much energy we're going to get from burning a tank of gas? And the answer is yes. So that's what this chapter is going to start looking at. So for chapter 7, thermochem, we got to go through a couple of our definitions. And we've seen these, right? Kinetic energy is our energy of movement. Potential energy is our energy of position. Thermal energy is related to kinetic energy because it is associated with temperature, which again means it's associated with movement, right? Like we talked about with the KMT, the theory of kinetic molecular theory, that your temperature and your kinetic energy, they're directly related, right? Temperature goes up, kinetic energy goes up. Chemical energy, this one's a little bit different, and we're going to look at this too. So thermal is kinetic. Thermal, I always think temperature, right? The other one we've got here is chemical energy, which is the energy that is stored in the bonds. So that means it's potential energy, right? It's stored in the chemical formula. Like for example, when I have a water molecule, we have an oxygen bonded to 2 hydrogens. There is energy stored in that bond. And if I break it, I've got to put energy into it. And then as it forms new bonds, it will release energy. But this chemical energy, it's potential. It's kind of being held by the molecule, right? Like we understand with the combustion reaction with propane or octane, right? We can get energy out of that. That's that chemical energy based on bond energies. So we're going to look at that in this chapter as well. Now, internal energy, I don't really worry about that one too much. I just kind of want you to know thermal is kinetic, temperature, movement, chemical, potential energy based on like your chemical formula, your structure, energy that's stored in there. All right. One conversion that we will use is that a calorie is 4.184 joules. And those are both units of energy. And it's just like if I said a kilogram is 2.205 pounds. Those are both units of mass. So the calorie and the joule, those are both units of energies. Now, in our calculations, we typically stick with joules. When we are going to be doing any kind of thermochemical equation, looking at heat capacity of solids or liquids, we always get our answer in joules. but calorie is probably something we're more familiar with, like with nutrition. Now, the other thing you'll notice, and this is, I know I never understood why this was like this, is that if you look at your nutrition labels and you want to look at how many calories you've consumed, really what you're being told on that nutrition label is calorie with a capital C, and a calorie with a capital C is equal to 1,000 calories with a little c. So in other words, it is really a kilocalorie. And I remember when I went to Ireland and I was looking at nutrition labels, just because I don't know, I look and read it all sort of various things. They actually label it as kilocalories. I don't know why we don't, but instead we make this weird distinction where we give it a capital C rather than a little c. But anyway, so when you see a capital C calorie, it's really 1,000 calories. So somebody asked me a question once, like if you eat ice cream and it's cold, we know that if we're going to heat that to body temperature, we have to put energy into it. So you consume this ice cream, it's heating up, that heat's coming from your body. So in a way, you're using energy, calories, to heat the ice cream. So does that offset the calories that you're eating? And the answer, of course, is no. And I could do that. We could do that calculation if we have the time, but it was a funny question. Anyway, so law of conservation of energy says that as we go through any kind of chemical change, chemical reaction, energy cannot be created or destroyed. It's only an exchange. It can go from the system, which would be the chemical reaction, into the surroundings, right? So we know some chemical reactions release heat. Sometimes they absorb heat, but there's a system, which is the change that's occurring, could be physical, could be chemical, and the surroundings. What's happening to the surroundings? Is it getting hotter or colder? So energy can just be transferred, but it can't be created or destroyed. Like you can't just say, poof, all the energy's gone. Well, it had to go somewhere, right? Now, heat and work, I don't really get into that too much either. All right. So if I'm just highlighting what I need you to know, we talked about thermal, chemical, and the calorie, the joule, the law of conservation of energy. Those are the ones I want you to make sure you're familiar with. The first law of thermodynamics is the study of energy, and it says that the total energy of the universe is constant. Again, we can move it around, we can exchange it, but the total energy of the universe is constant. And again, energy cannot be created or destroyed. All right, heat. All right, heat is the exchange or transfer of thermal energy, right? Temperature energy between a system and its surroundings caused by temperature difference. All right, so heat, the only reason why I'm highlighting that is because a lot of times students sort of oversimplify heat and they think, oh, temperature. But heat isn't. It's actually heat is actually energy, whereas temperature is just like Celsius, Fahrenheit, Kelvin. Heat is calories, kilocalories, joules, right? So it's a form of energy. And that energy exchange happens between the system and the surroundings. Okay, so chapter 7 is looking at all of this. So if I go to the next page, what we're going to start with is heat capacity or specific heat capacity. There's two that we have to think about. All right, so example here. Let's say I'm going to go and heat water and I want to heat it to boiling. And my question is, okay, how much energy should I use to heat the water? Well, my first question would be, well, how much water do you have? Right? Do I have a cup of water? Do I have a liter of water? Do I have a gallon of water? Right? More water means more heat. So more calories needed or joules to heat up a gallon of water than to heat up a cup of water. That makes sense. So how much is important? The second thing is, what temperature change am I trying to achieve, right? So delta T, change in temperature. Am I trying to raise the temperature just 10 degrees or am I trying to go 100 degrees, right? So if I have a bigger temperature change to achieve, it's going to take more energy. And then the last thing is, what is the substance, right? Because some things heat up pretty quickly and some things don't. Metals, like we talked about back in chapter 1, they are good conductors of energy. That's why we use them to heat our food. because they're going to transfer the heat from the stove or whatever, not the microwave, but from the stove or the oven, and that'll take that energy from our heat source and transfer it to the food. So they heat up really quickly. Water is a pretty good insulator. It takes longer to heat up, as we know, right? Watch, trying to boil water, right? It takes forever. So it depends on your substance. So there is a specific heat capacity calculation that we're going to do. And there's also a heat capacity calculation that we're going to do. So what's the difference? Because they sound really similar. All right, so let's talk about specific heat capacity first. The specific heat capacity, if I look at the formula down here at the bottom, the specific heat capacity, this is what we're going to use if we're talking about a specific substance like water, right? Heating that water, like we just talked about, boiling water. Well, we need to know how much water do we have? Do we have 100 grams? Do we have 1,000 grams? Right? So mass is the first thing we need to know. We talked about change in temperature. Are we trying to go up 10 degrees? Or are we trying to go up 100 degrees? The C, right? That's the constant. And that is specific to the substance. So the constant for water, the C, it is 4.18 joule per gram degree Celsius. All right. Now, you'll notice that in this first example, that is the specific heat capacity or our specific heat of water. This is only true for water. If we're looking at a different substance like lead, Pb, right? It's a metal. It has a much lower heat capacity. It is 0.128 joule per gram degree Celsius. Metals have very low heat capacities because that means it takes very little energy to start raising their temperature. Whereas water, an insulator, it takes a lot of energy to start raising the temperature. So this constant, the C for water, says I need 4.18 joules to take 1 gram of water up 1 degree Celsius. So a lot of energy. Okay. Now, the system, this happens when you have what's called a calorimeter. And the calorimeter, there are different types of calorimeters. One of them, it's always, it sounds like it'd be super fun. It's called a bomb calorimeter, and it's used for combustion reactions, right? Burning. Capacity and melting point. Not necessarily. Melting point, the question was, is there a relationship between heat capacity and melting point? And it's not exact. I can do a little bit more research with that and just say maybe if we limit that question to just metals, there might be a relationship, but in general with substances, there isn't a relationship between the capacity and the melting point. Melting point depends on what type of solid it is, what the structure is. So if you could narrow it down and say, okay, we're only talking about metals, then let's talk about heat capacity. So I'll look that up and I'll get back to you. All right, so the calorimeter, bomb calorimeter, you can have it on the way I thought about when I was first learning it is like, let's say you've got a Yeti bottle or those, you probably don't know the old school thermoses that I used to have in my lunchbox when I was a kid. So let's go with a Yeti bottle or a Stanley, right? Something that is sealable. It's an enclosed system. And what'll happen is if we call that the calorimeter, it's a system. And what'll happen is it'll give you the constant for the system. So it says, okay, if you use this Yeti bottle as your calorimeter, we know that for this change in temperature in that system, there was this much energy put in or taken out, depending on whether temperature's going up or down. So what you'll notice is in the formula, mass is no longer relevant because in the system, that mass, it's not needed because that calorimeter constant has already been determined. So every calorimeter would have its own constant, right? Every bomb calorimeter has been calibrated to have its own heat capacity constant. So it just now, if you think about it, the Yeti bottle, if I find the calorimeter constant for that, I'm using that particular bottle. So the mass of the bottle doesn't matter. I'm just looking at the energy that's happening, the change, right? That's happening inside that Yeti bottle. It's a sealed system. So you'll notice in the units, it's just going to look a little bit different. For the calorimeter, the constant is going to have units of either joule per degree Celsius or calorie per degree Celsius. And if it is a substance, now mass matters. So you're going to have grams in there as well. And the constant will always be given. So that's the question in the chat. And that's a good question. The constants, you don't memorize these. These would always be given to you in the question. Same with the calorimeter, right? Those constants, substance specific or calorimeter specific, they're always going to be given. So here's our first example. How much heat in joules would it take to raise the temperature of 814 grams of water from 18 to 100 degrees Celsius? There's that constant, the heat capacity for water. That's our 4.18 joule per gram degree Celsius. So this is our formula. Q equals MC delta T. So I always call it the MCAT formula, right? Kind of looks like MCAT. It's just that's not an A, it's a delta sign. So we need, and your heat capacity constant really tells you here, I'm looking at joules and I need to know the mass and I need to know the change in temperature. So the mass right here, 814 grams. So we know that's going to be our M. The only thing we're going to have to do up front here is find our delta T. So delta T is always final minus initial. So we are ending at 100 degrees Celsius. We started at 18. That's a difference of 82.0 degrees Celsius. That's our change in temperature. So we're trying to take 814 grams of water. We're trying to do an 82.0 degrees Celsius change in temperature. And our constant says we need 4.18 joules for each gram to go up 1 degree Celsius. So basically all I need to do is take that heat capacity constant for water, the 4.18, multiply it by the total mass that I have, the 814 grams, and then multiply that by the change in temperature I'm trying to accomplish, which is 82.0 degrees. Calculator, okay, got a big number here. I only want 3 sig figs, so 279,000 just for the placeholders. So 279,000 joules. So Q is our heat, right? Our energy. That would be the amount of heat energy we would need to apply to 814 grams of water to go from 18 to 100 degrees Celsius. So as we were talking about, if we had less water, less mass, less heat needed. If we only wanted to go from like 88 to 100 degrees Celsius, where our change in temperature was only 12 degrees, less temperature change, less Q, less energy required. Now let's look at an example with lead. Now we've got a 454 gram sample of lead. So there's my mass. Notice the heat capacity constant, much less. We talked about that earlier. Metals have much lower heat capacity constants because they are very good conductors of energy. The initial temperature here is 22.5 degrees Celsius. And if we apply 4.22 kilojoules of heat, what will be the final temperature? So we're looking for the final temperature of the lead. Slightly different problem. Same formula. So you know if you've got the heat capacity constant, you're going to be looking at the MCAT formula, MC delta T. The only difference here is we actually know Q, we know our energy, but what we're going to have to figure out first is what is that change in temperature we expect. All right, so the only thing is, really quick, the Q was given at 4.22 kilojoules, but my heat capacity constant is in joules. So I'm just going to really quickly multiply that by 1,000 to get it into joules. So I have 4,220 joules. So that's my Q. So if I'm solving for delta T, Q, divide both sides by M and C, that'll get me my delta T. So I have 4,220 joules divided by the mass of 454 grams and our constant of 0.128 joule per gram degree Celsius. So if I take 4,220 divided by 454 divided by 0.128, I get 72.6 degrees Celsius. All right, now that is my change in temperature. That's not my final temperature. That's just the change. So if I think about it, what I did with this lead, if this were my thermometer, right? I'm starting out at 22.5 degrees Celsius. That's what the question told me. I started out at 22.5. I put in 4,220 joules and the temperature went up, and I want to know where my final temperature is. What I know is that along the way, I added 72.6 degrees, right? That was my delta T, my change. So you can use the formula if you like. Delta T is final minus initial. That change is 72.6. So if I say, okay, final temperature is what I don't know, it would be 72.6 and then adding the initial temperature to both sides, right? Adding TI and adding TI. So your change in temperature plus where you started. I started at 22.5. My temperature went up 72.6. That means my final temperature ended up at 95.1 degrees Celsius. So that's where my final temperature for the lead would have ended up after putting in 4,220 joules of energy. All right. But for both of these questions, when you see that specific heat capacity constant given, right, you know it's going to be that MCAT formula. So you're going to need mass because you see the unit of grams. You're going to need delta T because you see, right, the change in temperature, Celsius, and joules, right? Those are how they're all related. So you got Q equals MC delta T MCAT. Now the calorimeter, what I had mentioned was that unit, that's going to look a little bit different. The calorimeter, that's the closed system. So this is like the Yeti bottle or the thermos, right? And in this case, what we would have is that closed system, whatever it would be. And in that bomb calorimeter, your heat capacity constant that would be given, that only applies to that particular calorimeter. So the units here are just going to be in joule per degree Celsius. And so if we know that calorimeter constant, and we know the change in temperature that happened in the calorimeter, we can figure out the joules. So mass for the calorimeter is not a factor. So you'll see that that unit is missing from the constant. All right. The bomb calorimeter, that's when we like to do like basically, combustion, explosions, right? Bombs, something like that, combustion. All right. And then produces a lot of energy. Okay. So next example is a good place for me to come back after a quick break. We're going to do this actually exactly in lab, the sample of iridium question. So I know we're heading out a little bit early, but if I start it now, we're going to be definitely late. So let's take a break. We'll come back into the second room at 12:30. So I'll see you shortly in part 2.